Hi, my name is Ignatius Bunk, and today we're going to talk about the difference between the orbital energy diagrams of hydrogen and carbon, and it's mostly pertaining to shielding and penetration. Now, monoelectronic systems are atoms or ions that have only one electron. In a polyelectronic system, for instance, carbon, they are systems that have two or more electrons. So keeping that in mind, we take a look at hydrogen, which of course is a monoelectronic system with the electron configuration of 1s1. Now, this single electron occupies the 1s orbital. And if we take a look at this orbital energy diagram, one of the things I would like to point out to you is that energy increases as the quantum numbers increase. Is quantum number 1, 2, 3, 4. So what I want to show is to see the single electron right here. That arrow represents a single electron, and it also shows the direction in which it is spinning. And this is that 1s electron, the electron that's in the 1s orbital of hydrogen. And if you notice that, look here at the n equals 2. See the 2s orbital and the 2p orbital, they both have the same energy. And also you see the same thing with the others, 3s, 3p, and 3d, same energy. Same thing here, 4s, 4p, 4d, 4f. So this diagram's actually, this is hydrogen in its ground state. Now, so that tells us that orbitals with the same quantum number have the same energy. And so those orbitals are known to be degenerate. So degenerate orbitals, so in monoelectronic systems in a ground state. And this is due to the fact that we don't have any other electrons in the system. And these electrons, if present, what they do is they cause shielding and penetration effects. And the way they do this is because when you have other electrons in a system, they exhibit the potential for like a repulsive energy from one another. So we have repulsion in the mix, and when that happens, and we don't know the path of these electrons, when that happens, we don't have degenerate orbitals. But and in this case we do, and we have a lack of shielding and penetration in this system. So we'll take a look at the hydrogen. Well, of course, hydrogen's ground state, but we'll take a look at these electron density, these electron probabilities. So we can see the density. The electrons are most dense, very close to the nucleus for hydrogen in its ground state. As well, you can see here, look, very close to the nucleus. So this one, if you look at this one, this is the radial probability. And you can see the maximum probability is not far away from the nucleus. It's right next to it, right on the outside. So one thing to take home from this is, again, we don't have the other electrons in the system that causes the shielding and penetration effects. So we have those electrons, or in this case, the electron, in the 1s shell, the 1s orbital, and it is really close to the nucleus. So that being said, we'll take a look at a polyelectronic system. Now this polyelectronic system, this is carbon, and it has a total of 6 electrons. And the electron configuration is 1s1, 2s2, and 2p2. So that means we have, you can see here, this is the orbital energy diagram for carbon, And this one here I just pulled from the previous slide. This is the one for this is the monoelectronic system, hydrogen. So you can kind of look at it for comparison. So, excuse me. That being said, we have carbons. The 1s orbital is completely full, as well as the 2s orbital, and the 2p orbital is only partially full. So, one thing you can look at this and see is that there's a big difference. These in hydrogen, see here, the degenerate orbitals, we don't experience that in a polyelectronic system. So we have a difference of energy levels with for orbitals with the same value in. And when we have something, when that happens, the energy levels are going to change, and that would, of course, give us a different radial probability graph. And that's one thing I wanted to show you guys. When comparing to it, I brought this from the previous slide. This is carbon again. And this one is a radial probability graph, and look at this. Just as before, the 1s orbital has its maximum probability very close to the nucleus, like when we've seen the probability plots for hydrogen, which is a monoelectronic system. And of course, the 1s orbital is a lower energy. And one thing we say about this orbital, it has the ability to now, since there's other electrons in the system, it has the ability to shield or partially block an electrostatic attraction between the nucleus and other electrons in the outer shells, and it partially blocks or shields that potential that otherwise would have been felt fully if they weren't there. Now, if we look at this 2p profile, it's actually closer to the nucleus. Its maximum probability, look right there, the maximum probability is closer to the nucleus. Now, this might lead one to believe that the 2p orbital has less energy and over the 2s orbital. But this is not the case. If you take a look here at this little hump of electron density that's located very near the nucleus inside the 2s profile here, we actually say that it has the ability to penetrate this 1s orbital. So it has the ability to penetrate that orbital. So when that happens, and it's able to penetrate more than this 2p orbital, it actually it gives the 2s orbital a lower energy, because the fact that it only spends a very small time, but it's very significant. The fact that it's very close to the nucleus, it gets to pick up feel this electrostatic attraction or potential between the nucleus and those electrons, and that actually will give it a lower energy. So we'll have, in that case, the 2s electrons, or the electrons in the 2s orbital, have a lower energy than the electrons in the 2p orbital. So that being said, we see that monoelectronic systems like hydrogen and some other ions, they don't experience all these repulsion effects that other electrons exhibit to one another. And that causes, of course, we were saying before, the shielding and penetration effects. So therefore, the orbitals with the same quantum number in monoelectronic systems have the same energy. But polyelectronic systems like carbon, they have more than one electron, and the electrons exhibit repulsive effects, and that causes the shielding and penetration. Those repulsive effects allow the 1s orbital in carbon to kind of shield the outer orbitals. But the 2s orbital has the ability to penetrate and experience more of an electrostatic attraction or potential energy than the 2p orbital, in turn giving it a lower energy than the electrons in the 2p orbital. And that being said is the difference between a polyelectronic system like carbon and a monoelectronic system like hydrogen. And I appreciate you giving me the time to explain this to you, and I hope this was really helpful. And my name is Ignatius Bunk. Have a great day.